Okay, everyone, thank you so much for coming. It's 1 o'clock, so I'm going to go ahead and get started. Welcome to our webinar and workshop on proxy system modeling for lacustrine archives. My name is Sylvia D. I'm an assistant professor in the Department of Earth, Environmental, and Planetary Sciences at Rice University. And I'm co-hosting this meeting with a large team, which includes support from the National Science Foundation and also the Continental Scientific Drilling Facility. And I'm going to let my co-hosts introduce themselves now. Carrie, maybe you can start.
Yeah, thanks, Sylvia. So I'm Carrie Morrill. I'm a scientist at NOAA in Boulder, Colorado, and I have been using lake models for the past 25 years since I've been in grad school.
Jim?
Hello. Sorry. Hello, everyone. My name is Yuang Jiang. I'm a data scientist working at Rice University. My interest areas include high-performance computing, Earth system modeling, and machine learning stuff.
Hi, everyone. I'm Jim Russell. I'm a professor at Brown University. I am a paleoclimatologist and paleolimnologist, and started working a lot with Carrie and Sylvia using the lake model in our research to try to quantify things we observe in lake sediments. And so looking forward to hearing from all of you about your interest.
And hi, everybody. My name is Kat Kantner. I'm the Science and Outreach Coordinator for the Continental Scientific Drilling Facility. So I'll be here in the background if you have any questions or concerns. For today's webinar, we do have a Q&A widget at the bottom of the screen. So at the bottom of your Zoom, you should see a button called Q&A. That's where we would love for you to put in questions that you would like everyone to answer, and those should be visible to everybody once they're submitted. That way we can sort of keep track of things throughout the day. Thank you.
Great. So just a brief overview of our schedule. So we're going to start with an introduction to proxy system modeling, go over the lake, water, and energy balance model, and go through some example use cases. We're then going to live demo how to use the lake model and talk about how to make input files. And we'll wrap up with breakout rooms where you can come and ask us direct questions, including everything from help with installation to designing scientific questions for your research. So between 3 o'clock CST and 3:10, we'll take a coffee break and we'll come back to those breakout rooms afterwards. Just a few reminders, we do have a very high number of participants, so please stay on mute at all times, except during your breakout rooms. We will be monitoring the Q&A, which should be at the bottom of your Zoom. Instead of posting questions in the chat, please put your questions in the Q&A, because with so many people, it will be difficult for us to monitor all the questions coming in. So again, as Kat mentioned, use the Q&A function and we will be answering those in real time. Great. So I'm going to go ahead and get started. The outcomes of this workshop are to learn to use climate data and proxy system models for lake systems. And we want to teach you all how to run this lake's proxy system model in both Python and as a graphical user interface. The scientific outcomes are to understand how we can link climate observations and model output using proxy system models for lakes, and how this is useful and might be useful in your science. So our hope is that you'll be able to include this in your own research by the end of the webinar. We've created a large body of resources to get you started, and Kat has posted that Google Drive link in the folder. There you'll find links to be able to download all the model code yourself. There are user guides, readmes, installation guides. Many of these have videos, and we also have posted papers and user guides that will help you get acquainted with the lake model itself. So please familiarize yourself with those resources as we go along here today. So I'm going to start with an introduction to proxy system modeling and data model comparison. For those of you who are unfamiliar with proxy system modeling, I'll give an overview of how this works and how we build them for lake systems. And then I'll provide a few examples of useful applications. All right, so let's dive in. We have three types of climate data in our field. We have instrumental data from satellites and weather stations. We have general circulation models or climate models, which allow us to create predictions of future climate change. And then, of course, we have paleoclimate information from lake sediment cores or speleothems or ice cores. And our best bet at predicting future climate change and understanding future risk is really to be able to compare all three of these different types of data. But comparing these types of data has challenges. For example, if I would like to compare output from a climate model, I might have fields like temperature, precipitation, humidity, or wind speed. And our paleoclimate observations often come in the form of complicated geochemical signals, whether that's oxygen or hydrogen isotopes in ice or corals, or maybe magnesium calcium ratios, or Tex86 or leaf wax deuterium isotope ratios. And so these two products have a very significant language barrier dividing them, which prevents us from being able to compare them directly. So how can we bridge the gap between general circulation models or instrumental data and our paleoclimate observations? So what we usually do in practice is we create some statistical relationship between instrumental climate data and our paleoclimate proxy. So this is an example just from the NRC. If we have some proxy data on the x-axis and we have instrumental temperature, we can just use linear regression to create a statistical relationship that links temperature to our proxy measurement of interest. And we can use that to back out climate over thousands to millions of years. So if we come back to our language barrier, we have our paleoclimate observations on the right, our weather and climate observations in units of temperature and precipitation. And usually we use this inverse approach where we calculate the climate variable of interest, in this example, temperature, as a function of the proxy observations, whether that's tree ring width or again, oxygen or water isotopes. This is called the inverse approach. We can also use a forward approach wherein we take climate data like temperature and precipitation, and we actually forward model our paleoclimate variables of interest. So for example, I might want to calculate the oxygen isotopes in cellulose as a function of temperature or precipitation. And this is where we can break down the language barrier between climate models or weather observations and paleoclimate data. This forward approach is what we use proxy system models for. So now I'll quickly introduce what a proxy system model is. So consider the following simple example. A real tree is a very complex biological organism, and it records climate over time, but it is not a thermometer or a rain gauge. And so we have to be careful when we interpret signals from our complicated proxy archives and note that climate is transformed through these systems. So we can design a proxy system model or PRYSM tree, or a computer tree, if you will, that takes climate inputs like temperature and precipitation and predicts the paleoclimate fields like tree ring width or oxygen isotopes in cellulose. So a proxy system model is a forward representation for how the proxy works with consideration for complexity choices. One of the ways I teach my students to think about proxy system models is as if they were in a recording studio. So paleoclimate data really acts like a filter through the climate system. So we can think of our lake sedimentary archives as nature's recording studio. So it's not a perfect recorder of the original climate signal. Similarly, when a band enters the studio, they make recordings, and changes in small atmospheric pressure waves are converted to sound waves, and then that signal's emplaced via an electric current or a magnetic field, and ultimately is emplaced on some tape or some digital record. So that's the beauty of forward modeling, is just like we're tracking signals in a band recording in a studio, proxy system modeling allows us to try to track how every piece of the climate signal is ultimately recorded in our proxy data. And so we do this by building proxy system models to think about all the ways in which our proxies filter the input climate signal, excuse me. Mike Evans and colleagues designed this, this framework for thinking about proxy systems back in 2013 as being partitioned into the environment, a sensor, the archive, and an observation. This is a general proxy system model we can build to try to understand how the signals we're interested in, changes in the environment, are ultimately emplaced in the observations that we make. So I'm going to step through each of these one at a time and give examples. An example of a sensor might be coral skeletons, which record the oxygen isotopes of the seawater in which they are forming as a function of temperature. So the environmental condition in that case would be changes in ocean water temperature. The sensor is the coral itself. An archive might be something like a sediment core, which is where the actual measurement is emplaced. And then finally, the observation is, what do we actually measure in the lab? What is the geochemical measurement that we're taking back and relating back to climate? And so there's a very helpful table, which I can share later, for how we build proxy system models. And in this webinar, we're of course focused on lakes. So in the case of lakes, which are listed at the very bottom here, we can think of the environmental changes that we're interested in as being, for example, temperature or precipitation. You might be interested in a different environmental change in your research. The sensor is the lake system itself. An archive might be a vegetation signal or another proxy that is recorded in the sediment. And then the observations we make might be pollen assemblages or plant functional types. So these are the kinds of ways we can start to divide what happens between the actual environmental change and the observations we make. So proxy system modeling is geared towards understanding the processes that govern transformations between the environment, the sensor, the archive, and the observation. So let's give an example. What are the impacts of environmental, but maybe not climate processes that might govern the formation of the proxy? So we have these three submodels that we can use to understand that. As I mentioned earlier, and I gave an example for corals, the sensor model might help us understand how does the sensor behave in response to some environmental forcing. So the sensor piece of a proxy system model is the physical, chemical, and biological components that might have multivariate, seasonal, or nonlinear responses to environmental changes. This is how is the proxy itself responding to climate. The archive describes how the sensor is either created or emplaced or recorded in the archive. So the output of the sensor is imprinted in an archive. Lake or marine sediments are a great example of this, because we're not actually measuring the mud itself, right? We're measuring geochemical signals or sensors within that archive, which is our sediment core. And then finally, we have an observation model, which is how do we actually make the measurement on the archive? This is where we have to consider things like age uncertainties or analytical uncertainties on our instruments, for example. So now I'm going to walk through how we build proxy system models for lake systems in practice. So as we've just seen, proxy system models are process-based forward models for paleoclimate archives. And since you're at this webinar, I think we can all agree that marine and lake sediments have provided some of the most crucial records of climate that we have on multiple time scales. And so what we'd like to do is build a full proxy system model that allows us to evaluate these records at a higher level, understand their uncertainties, and help us compare them to, for example, paleoclimate model simulations. So in this webinar, we're going to talk about different proxy system model functions that we've built for lakes, including a hydrological and energy balance model, and then sensor models for a number of different types of proxy data, such as the delta D of wax, oxygen isotope and carbonates, or GDGTs. So I want to walk slowly through the models that we have available for each of these different parts of the system. So keep in mind, again, that a proxy system model mathematically encodes our understanding of all of the geochemical and biological processes by which climate is imprinted and subsequently observed in proxy archives. In a lake system, the environment is actually quite complex. We have many processes that affect the energy and water balance of our lake systems. So the environment where we start is actually something that requires a pretty large modeling effort in itself. So let's start here. If we think about a lake system, we have to think about the water coming in and out. We might want to consider the oxygen isotopes or the water isotopes coming in and out of the lake. We might want information on the energy balance and the temperature profile, which is controlled by many different climate inputs. And whether we're interested in fields like temperature or salinity or mixed layer depth, we need to be able to simulate all those processes and how they might affect our paleoclimate data interpretation. So for this webinar, we want to introduce our lake environment submodel. So this is a lake energy balance model that was adapted by Hostetler and Bartlein. I'm only going to do a brief overview here since Carrie will provide a very detailed overview of the environment model. It simulates temperature profiles, mixing and eddy diffusion, radiative balance, lake level and water balance, and water isotopes. And so this forms the environmental component, the lake model, of our proxy system model for lacustrine archives. The original publication has some examples where for here on the left side, they're simulating temperature, so the lake temperature for different months and different seasons. This is for the Salton Sea in California. And essentially they're just solving, conservation of heat, et cetera, for a lake system. So this is the lake environment, which again, we'll dive into in more detail in just a bit. How might we think about sensor models? So there are many different climate archives in lake sediments. Many of us might measure bridge GDGTs, for example, or carbonates or delta D of wax. So within lake sediments, we actually commingle many different types of sensors. And the way we've designed the proxy system model is such that each proxy has its very own sensor model. So this is a flowchart from Dirk Saxe's review about delta D of wax proxies. And we have a physical understanding of how this proxy works. We know that there are impacts on source water, which are affected by things like temperature and precipitation amount. We have an understanding of how the plants itself transform that signal into the actual measurements we ultimately make. So there's a sensor model that's been built specifically for the delta D of plant waxes, published by Bronwyn-Konecki et al. In 2019. And so this sensor model takes precipitation water isotopes and transforms that into wax delta D. And so all of the ways in which that initial water isotope signal is transformed into leaf wax delta D are represented in this sensor model. So this is an example of one of the types of functions that is built into our proxy system model. The other thing you'll find in our sensor models is functions that allow you to assess the uncertainty in things like temperature reconstructions. So these two examples here are from two papers that we've used as examples to try to understand the errors in bridge GDGT reconstructions. And so essentially, the sensor model will convert your temperature into a GDGT time series, and it will also produce 1 sigma bootstrapped errors such that you can account for some of the calibration errors in your time series. Moving on to the archive model, sensors are deposited in the sediment, and after that occurs, there can be post-depositional processes that alter the signal. For example, a bioturbation model or a compaction model might be included in the archive model. So again, recall that the archive model describes all the ways in which the signal is placed in what we measure. And so in this case, we're looking at a sediment core. That's our archive. After your proxy sensor has compacted into the sediment, it's going to be affected by post-depositional processes. And so we can simulate compaction and bioturbation directly to see how your time series might be affected by those post-depositional processes. In our current model, we have porosity and sedimentation using 2 published models. We're just building off of previously published work, including Barr et al. And Hybers and Wunsch. So this figure on the left just shows an example output from the archive model. This is the porosity profile in the sediment core, which you set as the user. And then on the right here is the thickness / the depth of the compacted layer versus a non-compacted layer. So we're actually able to directly simulate the relationship between depth and sediment height before and after sediment compaction. And that's the function of porosity. So again, this helps us understand some of the post-depositional processes that might alter our interpretation of the signal. Another post-depositional process that goes into our archive model is bioturbation. So here I've just adapted a MATLAB model published by Martin Trouth. So many of you may have used this before. It's Turbo 2. So we've converted this into Python for the lake proxy system model. This just shows 2 examples from the output of Turbo 2, where the original isotope values are shown in black and the bioturbated isotope values are shown in blue or red here. And so you can use the model to estimate uncertainties that might be driven in your signal by bioturbation alone. Finally, moving on to the observation model, we have to account for things like analytical uncertainties and age uncertainties or dating uncertainties in our data. And so the lake proxy system model has functions that allow us to explicitly simulate age model uncertainties. We use bcron, but of course there are many other softwares out there that allow us to simulate age uncertainties. And really you can use whichever you'd like, but this is the particular model we have included. So putting all of these together, we can look at all of these different proxy-specific and sediment depositional processes that affect lacustrine sediments. We can predict the relationship between temperature, for example, and different sensors like TEX86. We can look at the impacts of sedimentation and compaction via the proxy system archive model. And then we can directly simulate analytical and age model uncertainties. Bringing all of this together gives us a full proxy system model for lake sedimentary archives. It includes the environment of the lake system and the climate system. It includes multiple different sensors. Many of these can be added if you have more ideas for different functions, and I'll talk about that later. It includes archive-specific changes like sedimentation, compaction, and bioturbation. And then finally, it allows us to evaluate the impacts of dating and analytical uncertainties. So from here, I'm going to turn it over to Dr. Carrie Morrill. I hope I've convinced you that we can build very intricate models that help us connect climate model output or instrumental climate output to the observations we make by simulating all of the different ways in which our proxy systems transduce the original climate signal. So now we're going to do a deeper explanation of the lake environment model. So I'm going to stop sharing my screen and turn it over to Carrie.
Thanks, Sylvia. I'll bring up my presentation. Okay, as Sylvia mentioned, I'm going to be describing in greater detail the lake environment model. So, of course, this is the physical lake system that the sensor or proxy experiences. And it includes variables like water temperature, salinity, isotopes, lake level, ice cover, and mixing. But before I dive in, first I wanted to point out the original development work on the environment model. And this is a one-dimensional lake energy balance model that was developed by Steve Hostetler and Pat Bartlein in the early 90s. And I've listed a bunch of references here as documentation for the model and different model sub-modules that they added through time. And also just wanted to emphasize that it's very important to cite one or more of these references as appropriate, along with Sylvia's 2018 paper about the entire proxy system model if you're using the lake environment model in your research. So detailed view of the lake environment model. So the model looks like a series of levels in a lake, which are generally about 1 meter thick. And the energy balance is calculated through looking at lake atmosphere exchanges of shortwave radiation, long-wave radiation, latent heat, and sensible heat, which impacts surface temperature. And then mixing in the model, both eddy diffusion and convective overturn translates these temperature anomalies, the heat anomalies, to deeper levels of the lake. And there's a couple optional submodules that can be turned on and off by the user depending on your application, including the ice growth and ice melt, the water balance, the salt balance, and the water isotope balance. And in the next few slides, I'm going to kind of walk through each one of these different subcomponents in a little bit more detail. So first, the lake physical setting and initial values. So as I mentioned, it's a series of about 1 meter deep layers. The user has to specify a couple of kind of physical setting parameters, including the elevation of the basin bottom, the initial lake depth, and the sill height above the basin bottom. And then there are initial values that have to be set for each of the layers of the lake, including the area, an initial value for temperature, salinity, and isotopes. Those are optional, depending if you're using those submodules. And in general, it's possible just to set a constant value for each of these variables, and then the lake system will evolve during a spin-up process. 2 other parameters that have to be set are the latitude and the total basin area. So that's lake plus catchment, which is important for the water balance. Now, in terms of the surface energy balance, as I mentioned, it's the combination of shortwave radiation, longwave radiation, latent heat, and sensible heat. The arrows here in gray are values that are input to the model by users, and the values, the arrows in orange, are the fluxes that the model is calculating. So for shortwave radiation downwelling, shortwave radiation is input to the model through a model input file, and the model calculates upward shortwave radiation as a function of the day of the year and ice cover. There's also shortwave absorbed into the water column, which is calculated as a function of the shortwave extinction coefficient, which is the parameter set by the user. For long wave radiation, downward long wave radiation is input to the model by the user, and upward is calculated as a function of the lake surface temperature via the Stefan-Boltzmann law. For both latent and sensible heat fluxes, these are calculated by the model as a function of the respective air to lake gradients in specific humidity and in temperature, the wind speed U, surface pressure, and a drag coefficient that's specified by the user. So one thing that's really important to note here is there are these two very important user specified lake specific parameters, the neutral drag coefficient and the shortwave extinction coefficients. There are ranges of kind of acceptable values for these parameters, but some amount of calibration is necessary as well in order to get a reasonable simulation of your lake. In terms of mixing, the model simulates two different types of mixing: eddy diffusion, which is parameterizing or kind of incorporating the effects of turbulence. This is calculated from the heat diffusion equation using an eddy diffusivity parameter, and that parameter is calculated by the model, and it's a function of latitude, wind speed, and the presence of lake ice. In terms of convective mixing, this happens when the density of one layer in the lake, which the density is being calculated by the model from temperature and salinity, is greater than the density of an underlying layer. And so all layers with a density and stability are then mixed. So now I'm going to talk a little bit about the optional submodules of the lake environment model. The first one is ice growth and melt. Ice growth will occur in the model when lake surface temperature is below the freezing point of water, and the freezing point of water is a function of temperature and lake salinity. The ice initially grows in a 1 centimeter layer to cover the lake, and once the lake is fully covered, the ice can grow thicker. Once ice is covering the lake, any precipitation falling on the ice accumulates as snow. Melt will occur when the snow and ice temperature is greater than 0 degrees Celsius. Snow melts first, then ice. And once the ice is less than 1 centimeter thick, the ice fraction will shrink from 1 being fully ice covered to 0 being fully ice free. So simulating ice and snow is important for a couple different reasons. First, these increase the surface albedo, causing greater reflection of shortwave radiation from the surface. And ice and snow also insulate the lake water from the atmosphere, causing the surface energy balance to be taking place at the ice air or snow air interface rather than at the lake air interface. So the second optional submodule I'll be talking about is the water balance. And that's shown here in these arrows. So the gray arrows are values that are input to the model as part of the input file, and that includes precipitation and the catchment runoff. The runoff includes both overland and groundwater inflows. The model calculates evaporation and condensation. It's the latent heat flux in the model, and also calculates spill from the lake. So any lake level rise that occurs above the sill level is converted into overflow and is output as a spill value. And lastly, if the lake dries up, the simulation will stop. So if you're doing water balance calculations, you can also run a salt balance. And the lake salinity is tracked at each layer of the lake. Lake salinity is increased by evaporation and also a salt term that's input for the catchment runoff. The lake salinity is decreased by precipitation and fresh runoff. Salinity is important in the model because it impacts the water density for mixing, evaporation rates, and the freezing points for ice formation. Salinity is mixed across the layers of the lake by both eddy diffusion and convection. And the last optional submodule I'll talk about is the water isotope balance. This again requires water balance calculations. And the isotopes are tracked in both the precipitation inputs, so that's provided by the user, the catchment runoff inputs provided by the user, and fractionation occurs during evaporation that's calculated by the model. And the isotopes are tracked at each layer of the lake. And the isotopes are mixed across these layers by both eddy, diffusion, and convection. So in terms of output variables, what the environment model will output, I think currently it's configured to output surface temperature and the temperature profile through the lake, the evaporation rate, average and maximum mixing depth for whichever kind of averaging period is being output in the output file, the latent heat flux, the sensible heat flux, the surface net shortwave, and the upwelling long-wave radiation. So you can kind of track what's happening with the surface energy balance. From the optional modules, it's possible to look at ice fraction, ice height, snow depth, the lake depth, the overflow, and the surface water isotope values. So last, I just want to kind of summarize and point out, every model is an approximation, and this model is also an approximation, is not perfect, and kind of point out some considerations that you might want to think about as you're applying this model to your particular lake. So first, this is just kind of a general comment. There's general limitations with single column or one-dimensional models like this one is. Namely, there's no horizontal motions or horizontal heterogeneity simulated. This is generally not a problem for understanding the general energy or water budget of a lake. But if you're trying to simulate a lake with large horizontal heterogeneity, it could be more difficult to compare the outputs of this model to a specific core site. I also wanted to point out that it's been reported that there's some underprediction of mixing in large and deep lakes. And I would direct people to this paper by Zach Subin, published in 2012, discussing possible ways to work around this, including increasing eddy diffusivity values. There's also currently not a way to model groundwater outflow in this model. It's only surface overflow through a spill. So it is possible to add this in offline water balance calculations, but it's not part of the model at this time. It's also been pointed out that the lake ice fraction in this model is generally either 0 or 1, making it difficult to simulate periods of fractional ice coverage. The ice kind of transitions very rapidly from periods of completely ice-free to complete ice cover. And there's also currently in this configuration, no simulation of storage and release of heat by sediments. And this is particularly important for shallow lakes, where shortwave radiation travels throughout the water column and can heat the sediments at the bottom of the lake. And of course, there might be others depending on your application. So that is my summary of the lake environment model. Some things to watch out for, the things it's good for. Hopefully it's got you thinking about how you could be using this model for your application. So I'll pass it back to Sylvia.
Great, thank you. All right, let me get back up online here. Carrie, can you confirm, are you seeing my slide and not the prep slide? Great, thank you. Okay, I see there are lots of questions coming in the Q&A as well, which is great. We promise we'll get to everyone's question. Just give us a few minutes and hopefully we'll hit them all, but keep them coming. All right, so let's talk about a couple full PSM use cases. And I'm loving the questions coming in because I can tell you're already thinking about what kinds of scientific questions we can use this model for. So coming back to this full schematic that I showed earlier, the idea of using the lake proxy system model is to understand how signals are propagated through each part of this system. So whether you're interested in, for example, how air temperatures are transformed by the lake system into lake temperatures, whether you're interested in how the proxy system itself is sensitive to climate or some of these post-depositional impacts. These are all questions that can be tested and answered. And a lot of the questions that are coming in, I notice, are specific to testing certain signals, like if there's a volcanic event, can you do that? All of that is just dependent on your input files. So as long as your input climate files are simulating the events that you want to track through these systems, then yes. So there's a lot of flexibility in how we design our input files and set up the model. And that all has to be done with a mind for how or what scientific question you want to test. But the idea is that we have built an ability to translate between climate data in units of temperature or precipitation and the ultimate proxy measures that we make. So this is our framework for data model comparison, right? This is a way that we can link output from climate models or instrumental data spanning the 20th century to observations of climate from our paleoclimate observations. So for example, on the left here, perhaps we're working with paleoclimate model output from PMIP 3 or 4, or maybe we're working with a transient simulation. The lake proxy system model can be used to then convert that climate model output into proxy units in the same level playing field, such that we can compare apples to apples. So instead of comparing temperature to delta D of wax, I'm instead comparing delta D of wax to delta D of wax. So we're comparing computer apples or simulated proxies to real proxy data. And that is really the motivation of all of this work, is to put everything on a level playing field and try to diagnose how the original climate signal of interest might be altered by these different processes that aren't ultimately related to the climate signal we're trying to measure. So I wanted to take a moment and have us think, what are the kind of key uncertainties that you handle in your work that might be related to your proxy system that you work on? What kinds of process-based models or submodels might enhance your research? I've showed the kinds of functions we have included now, but one of the things that I want to stress is this platform is designed to be user contributed and crowdsourced. So if you build a proxy system model or a sensor model that's specific to your research, you can build it into this framework and design a tool that will work well for what you need to do. And part of what we're going to do in the breakout rooms later is provide some assistance or feedback or coaching on how exactly to do that, because there's no shortage of additional proxy system models we might want to design to test some of our assumptions about our interpretations of our climate, paleoclimate data. So what is our current proxy system model missing? We haven't covered every single proxy type. And so I would urge you to take a couple minutes now to think about how you would design additional models into this framework. And so we're just going to pause for about 2 or 3 minutes. If you need to take a mental break or check your phone, I give my undergraduate students technology breaks. So we'll just pause for a minute or two to think about these questions. Okay. Great, so we'll have time to talk about your specific ideas a little bit later during the breakout rooms. So at this point, I'm going to transition to a live demo on how to use the lake model graphical user interface. And I'm going to introduce Vinay Tumarakota, who is a fantastic undergraduate student here at Rice University who worked with a team of students to design this graphical user interface. So thank you, Vinay, so much for joining us. And I'm going to stop sharing so you can take over.
Awesome. Hi, everyone. I'll just share my screen really quickly. Okay. Can everyone see my screen with the graphical user interface?
Yes.
Wonderful. So this is the graphical user interface, or GUI, for the lake proxy model. We can begin using the GUI by starting with the lake environment model. So the lake environment model basically consists of 3 steps. We first need to upload a text file to provide input data. We then need to enter lake-specific and simulation parameters. And then we simply need to save these parameters and run the model. So just to go through an example of that workflow, I have here a text file which I can upload that relates to data on Lake Tanganyika. And within the GUI, we have buttons to autofill the lake-specific, simulation-specific parameters for this particular lake. However, you are also free to use different values based on the parameters that are related to the lake that you might use. So I want to pick this value for this lake. And then once I've entered in all the parameters that I think will be necessary, I can save them and then run the model. And I'll receive a notification saying that the model will take several minutes, and I'll receive a notification once the model has finished. For the sake of time today, I won't run the model, so I'll click no, but if you would, then you can click yes. Additionally, if you try to enter any kind of non-parameters into the GUI, you'll be encountering a notification saying that the parameter that you entered is not a valid value. That's another way that the GUI can verify that the values that you've entered are correct. Additionally, if you'd like to save the parameter values that you've used, then you can once again click Save Parameters. And then if you want to refill the parameters that you've previously saved, you can click Autofill Previously Saved Parameters and notice that 22. And so this save parameters works only for a given instance of running the GUI. So if you exit out and then restart, then those parameters won't be saved from run to run. Will only be saved within the running particular execution, if that makes sense. So that covers the basics of running the lake environment model. So now we can move to plotting environmental time series and seasonal cycle data. So here I can upload an example file and then graph various metrics relating to the data that I've just uploaded, including surface temperature, mixing depth, duration, latent heat, sensible heat, downwelling short wave radiation, upwelling long wave radiation, and mixing depth. And if I'd like to save this data so that I can share it or perform more analysis, I'd be able to do so by saving it as a CSV. So I can save it here. And then if I go to my folders, then I'll actually be able to pull that up. So here's data.csv. And here I have my time unit and my y-axis. I'll also save this visual as a PNG if I would like to. Then once again, I can go back to the folder and see that the PNG is there. And then I can head back to the start. The environment seasonal cycle page is largely the same, except the unit of time is in months. Notice on the axis, it contains the same metrics and values. The next set of models are the sensor models. We have the carbonate, GDGT, and leaf. Once again, I'll upload an example file. And I can use various types of formulations of carbonate models. Citations are listed within the GUI if you'd like to investigate for further inquiry. Then I can generate graphs of these various models. You'll notice that the graphs have similar shapes, but the y-axis themselves is changing. And once again, you can save the data as a CSV, download the graph as a PNG, and head back to the start page. Additionally, if you are interested in investigating these further, these are actually hyperlinks that you can use and pull up the question, so that way it's easy to find the model. Next, we have the GDGT model. So here we have two types of GDGT models. We have the text86 models and the MBT models. The example file within the GUI is only applicable to the text86 file, or to the text86 models. We'll run it with that. Oh. And then generate graphs. Oh, sorry, and upload the file. Now it works. Yeah, so once you upload the file, then you can run the models and then graph them. And the MBT models actually take a separate type of file as input because of the fact that they require different input parameters than the text. So the same lake environment model input file actually applies to them. And once again, you have the citations available if you'd like to investigate these models further. Next, we have the leaf-wax model. The leaf-wax model takes its own distinct input file. You need to specify the year at which the file begins. So here it says 1953, so I'll specify that start year, and then graph the leaf-wax proxy data, which includes confidence as well. And importantly, when you save the data, then I can open it. And it will contain the confidence intervals in addition. Next, we have the archive models, which are bioturbation and compaction models. So we'll begin with the bioturbation model. The bioturbation model can take input from any of the three sensor models that we just went over, the GDGT, carbonate, leaf-wax models. Here I'll just upload an example file that contains output data from the leaf-wax. And so I'll specify start year, end year, and then mixed layer thickness coefficient. Actually, I don't remember the specific sample values that I used for this. But
You just go 1.1.
one for all three. Sure. Let's see. Well, I'm not quite sure what parameter values I used for this one for, but let me just put one for all three. Okay, yes. So yeah, I think it might have been the case that maybe some of the parameter values were incorrect, but with these sample parameter values, you can graph the bioturbated data on the axis. And then you can use the output from any of the three models, not just Next, we have the compaction model, which does not actually take a particular input. It simply takes certain parameters that you can use. So for the sedimentation rate, let's say 20, I have years across 5, generate some type of graphs that reflect the porosity of the model. And you can download these graphs once again, or save the data as CSV. And then if we head back to the start page, we then are left with the observation model, which is the final in our series. And so the observation model, we have another example file. And importantly, this model does require some amount of time, as was the environment model. So if I click graph observation model, it'll actually take a few minutes to run and then display me. So I won't have the time to necessarily show that here, but you'll be able to do so. And you can also see the result of the observation model in the tutorial video that's linked on the GUI website. That concludes going over the different models within the GUI. Know that that was a lot of information most likely, so there is a tutorial video that is posted to the website that goes over this information in as much or not more detail, and so you'll be able to follow along through those examples, walk through more of those. Yeah.
Thank you so much, Vinay. All right. So the next part of our webinar is going to be a tutorial and live demo for folks who might want to run the lake model in with a little more control outside of the GUI. So running it in Fortran. So I'm going to ask Dr. Yiyang Zhang to go ahead and show us how we would do that.
Hello, everyone. Can you see my screen? Okay, so now let's take a look at the Fortran version of a lake model. So on my screen, it is a model folder. If you download the code from the GitHub, it should be similar to this. So to run the model, you only need 3 files: the Fortran F90 file, an include file, and the climate input file. So please make sure the Fortran F90 file and the include file are both in the main folder, so the include file can be easily used by the Fortran code. And here we put the climate input in the input subfolder, and the output folder is temporarily empty. Let's start from the include folder, include file. We can open it using any text editor. So this is the include file. Let me zoom in the text. Okay. So you can see the first block in this file declares lots of variables, and most likely you won't need to touch them. So they are directly used by several subroutines in the Fortran code. And the second block of this file is called lake-specific parameters. So ideally for each unique lake, you need to modify the parameters values here. For example, the geolocation information, longitude, latitude, lake depth, lake area, and prescribed salinity, this kind of stuff. And you also need to specify the path of the climate input file. Like here, we put it in the input subfolder. And the third block here is called simulation specific parameters. So they are mostly module flags. For example, if you want to use the hydraulic module, you need to turn on the water balance flag here. It's called WB and score flag. And there are also some other modules here, like the ice flag, the salinity flag, and also you can specify how many years you want to do the spin up by assign value for the N spin. And the rest part of this file basically just some physical or chemical constants and common blocks, like density of water, ice, heat capacity of ice. You can check if you need to modify it or not there are comments. There is a comments in each line, so it should be easy to understand the parameters there. Okay, once we finish this include file, okay, yeah. So then we can start to prepare the climate input file. So the climate input file doesn't have a headline, but don't worry, you can find the headline information from the model GitHub page. And here I reopened it in Excel. So, okay. So you can see the first column is the year. Here we only have 2 years, 1, 2. And the second column, the date. For the first year, it's kind of like a DOY, but from the second year, you need to increase like 30 days by the end of the first year. Like here for each month, we increase from the 15, 45, 75. And from the third column, it's air temperature, relative humidity, wind speed, short wave radiation, long wave radiation, pressure. And you also have 2 optional inputs, which are precipitation and basin runoff. Basically, you don't need to pose the precipitation and the runoff here. You only need to use these 2 inputs when you turn on the water balance module. When you turn on the flag, then you need to pose these 2 optional inputs here. Okay, and here you can use the monthly mean climate to prepare this file. Okay, once we finish these 2 files, we can start the last one, the most important one, the filtering code. Okay, here I use the text editor, open it. Okay, here is the F90 file because it's quite long. And the only thing I want to find from this file is a path for the output files. So normally I just tap Control F and I search BAT. Okay, I found it. So it's in the line 784. And you will see there are 2 output files. The first one is called T-proof. It means the temperature profile of the lake. And the second one is called SURF, S-U-R-F. Basically, it's a summarized output for the lake surface, like lake surface temperature, short wave radiation, long wave radiation, and evaporation, this kind of stuff. So you need to specify the path of these 2 output files. Okay, once we finish all these 3 files, the F90 file, the include file, and the climate input file, we can start to compile the whole model. Here I'm using a Mac computer. So basically I just open the terminal or a client software. Here I use iTerm. Can everyone see the client software? Okay. So what I need is just CD to the main folder. And you can see the code file, the include file, and the 2 subfolders. So I just need to use the gfortran compiler. Dash lowercase o, and give the executable file a name. Let's call it PRYSM run, and post the forwarding code there. Okay, and enter. Okay. Now we can see the PRYSM run executable file is there. We just need to run it. Okay, so it may take a few minutes. And here I want to mention one thing. So each time after you modify the include file, you need to recompile the whole model. So not only if you modify the F90 file, definitely you need to recompile the model, right? But if you only modify the include file, you also need to recompile the whole model because the include file is directly used by the forwarding code. So it's kind of part of the code. Otherwise, you won't be able to use the updated parameter values. Okay. So here, I think we probably need to wait like 5 minutes. And because I finished a pre-run, so I can, oh, sorry. Okay. And you can see the output file are being generated in the output folder. If we directly open it by a text editor, okay, it still need time, but doesn't matter. I finished the pre-run. So the output files doesn't have headline. So basically it's only numbers. But here I manually add the headline in Excel, and you can see the first column will be day. The second column will be surface, lake surface temperature, and then mixing depths, lake evaporation, latent heat flux, sensible heat flux, short wave radiation, long wave radiation, maximum mixed layer depths, and the last one should be the lake depths. Sorry, the blocking. Okay, the lake depths. Yeah, but from the raw output file, there are no headlines. And again, you can easily find it in the GitHub page, so it should not be a problem. And both the input file and the output files are in text format. So you can use like Excel, MATLAB, or R, these kind of statistical software to do the plotting or analysis. Okay, that's it. So this is the 14 version of the lake model, and hope it's not too boring. And now I give the microphone back to Sylvia.
Great, thank you so much, Yi-Young. So those tutorials hopefully gave you a sense of what it's like to run these models in practice. I think, you know, it can be a big learning curve when we're learning to use new software or using someone else's code. So, you know, hopefully these tutorials make you feel a little more confident in, you know, once you have the model downloaded, knowing where to begin. All right, so I'm going to go back to my slides here. Okay, so we've gone through some demos of both the graphical user interface and the Fortran version. I wanted to just round out Yi-Young and Vinay's presentation by redirecting you back to the contents in the Google Drive folder. So all of these different versions of the model are there linked that you can download, and the README files, as well as a lot of documentation, is housed there as well. So we are getting a few questions in the Q&A about specific parts of the code or how it works. And so do poke around in the Google Drive and look at what we have there. But broadly, you know, we have all of this code up on GitHub. The original version of PRYSM, which stands for Proxy System Modeling, was designed to be an open source Python-based platform for paleoclimate forward modeling. And so both Carrie and I have GitHub pages, which we again have listed in the Google Drive resources, where you can go and download all of the model code for yourself. There are also other proxy systems that have models, not just for lakes. We also have models for ice cores, corals, tree ring cellulose, and speleothems. So there's some instructions on how to download all of these. And if you're working in a directory in a terminal window, as Yi-Young just showed, it's relatively easy to install these packages if you like to install them all at once. So yeah, so basically, if you go to the web page, I just wanted to show you what you would find. So if you were to go to my GitHub page, you'll find a sort of start page for PRYSM, where you'll find a folder that says PSM, so Proxy System Model. And this is the folder that you're going to want to navigate to to download all the code that we've been talking about today. When you click on that folder, you'll find that there are lots of different proxies represented here. There's age modeling software. You'll see the different sensor models that we talked about in the different proxy systems. For the purposes of this webinar, we're talking about this lake drive. So all of the lake proxy system modeling code will be available in the subdirectory called lake. And then, as we've just seen, and as Vinay nicely walked us through, we do have these graphical user interfaces. These are downloads that are executable. So you'll have to download the executable file and then run it on your machine. We went through all of this ourselves for both the Mac and the Windows and PC versions. And those executable files, again, are on the Google Drive. So you can go ahead and download those, and you should be able to run them on your own computer. And we are, of course, here, given that these are all still, in beta testing. We are not professional software developers at Meta, although Vinay is pretty close to New York as well. So we welcome your feedback to make these tools even better, and we are here to help if you run into problems. So as Vinay demoed, for all of these different GUIs or graphical user interfaces, you can configure them to be specific for your site or your scientific question. So all of them are going to have site-specific information and allow you to change and manipulate the input files. And we do provide example input files that can be changed at every step. There are also plotting functions. So I did want to just echo and remind everyone that these online GUI tools will do everything from plot a time series to calculate a power spectral density plot to simulate the age uncertainties and plot them. And you can actually download the figures directly to your machine. So you should be able to, do a lot of these modeling functions without doing it sort of in the command line. And you can also use this for teaching, which is a big hope that we have for this set of models. So all of this, a couple take-home messages here. What we want is to have models that help us translate between climate models or historical instrumental climate observations and convert that to proxy units. And we might think about this as sort of a flight simulator, right? We're trying to understand all of the ways in which the input climate variables are changed by these systems. And this is really a tool to try to build bridges between climate modelers and paleoclimate data generators. Our goal is to keep all of this as public and adaptable and modular as possible. So this online GitHub framework allows for people to contribute new models and to give us feedback on what we might want to include. But certainly for all the students or postdocs in the room, this is a great way to publish a model that might be useful to a wide array of other people in the community who are interested in similar questions. We do have several papers posted again in the literature folder for the Google Drive, and we'll continue to add additional resources there. But if you're interested and if you can look at the supplementary information for some of these papers, we have detailed readmes and guides that review all the things we just went over. So I'm going to pause here for just a moment for another 30 seconds so we can take another tech break. So check your phones. Check your email. Or stretch. I see a couple open questions. We are going to go through some example use cases in just a moment, so be patient. We'll get there. All right, so let's 2:15. Let's go ahead and keep going. So Yu-Yang touched on this a bit already, but I just wanted to go over in more detail how to create model input files for your own project or site. So if we come back to the lake proxy system model, you'll notice that there are a lot of components, and we have very detailed READMEs again that explain what input variables are needed to run the model. And in particular, in order to simulate lake energy balance or water balance, you do need to have climate input data, air temperature, pressure, radiation, surface humidity, wind speed. If you want to run the water balance or the water isotope balance components, you need to have the precipitation and runoff and the water isotopes in those fields. So different inputs are required depending on what you're hoping to gain from the modeling. This table shows all of the input fields. The fields listed in pink here are required for all functionality of the lake model. So the far left column, again, which you can alter very simply in Excel or any other text editor, is just year, day of the year. You need air temperature, relative or specific humidity, wind speed, incident shortwave radiation, downward longwave radiation, and surface pressure. For the water balance, precipitation and basin runoff are required inputs. And then for the water isotope portion of the model, you also need to specify the delta AT0 and delta D of precipitation and basin runoff. So in our example input files, which you can find on GitHub or in the downloads for the GUI, if you open one of these files, the input files, it's going to look something like this. So this is just an example for Lake Tanganyika. So you'll see in the far left column, it's year. There are 12 values. We're running this version of the model with monthly time steps. So we stay on year 1 for 12, we stay on year 2 for 12. The day of the year ticks forward. Temperatures come from either instrumental data or a climate model, as with all of these fields. So we're inputting monthly data to drive the lake model. All of these fields, again, can be readily edited from the example input files that we've provided. So a couple options that you have, you can open the example files in Excel, save them as a text file, just tab delimited. You can write these files in any standard programming language. In the Google Drive, I provided a Python script for how to take ERA interim reanalysis data and convert it into a lake model input file for a specific site. And you can also directly edit the example input files that we've provided on GitHub. Just be careful when you run the model that everything is formatted correctly, because Fortran can be a bit finicky if, for example, the tab spacing is incorrect. So always be careful to make sure the input file is formatted in a way that Fortran will recognize. There are a few different options for designing input files. And again, we've been getting quite a few questions about this. This really comes down to which time period are you interested in simulating and what data are available. So you can obviously use meteorological station data. We can use reanalysis data. So for example, NCEP, NCAR reanalysis or ERA interim. And then of course, there are climate model outputs. And since many of us in the room think about paleoclimate applications, there are publicly available simulations from the Paleoclimate Model Intercomparison Project. So these have different time slices like the mid-Holocene or the last glacial maximum. You can also use transient simulations like the Trace 21KA to get the variables that are needed and design input files from those climate models. So really, we are limited in whether or not we have physically consistent representations of climate inputs for the time period of interest. So, one of my collaborators on a different project is very interested in the last interglacial. So we tracked down a modeling group, the HADCM3L group, that had a last interglacial simulation, and we were able to run the lake model for that time period. So we're basically just limited by what climate inputs you can find and what time period they span. Okay, so now I'm going to show a few examples of scientific questions that we've used these models to evaluate in the past. And hopefully that'll be a nice lead into our breakout rooms, where you can talk through your own science and your own questions with all of us hosts. And so these are just a few examples that we've worked through in our research of how we can use the lake proxy system model to identify uncertainties in proxy interpretation, and also to just model systems that we're interested in. So as Carrie showed earlier, there are lots of different output fields that come from the environment model. We can look at lake temperature profiles. So this is depth here on the top left, and the season or the month of the year, January to December. So we can look at how seasonal lake temperature profiles evolve over time. We can look at lake temperature seasonal cycles for different climate models and how different climate models force the lake system. We can look at seasonal mixing depths, shown here on the bottom left. And we can also look at outputs like changes in evaporation over different time periods. But broadly speaking, the goal of all of these exercises is to try to make more informed interpretations of our paleoclimate data. So I'm going to go through 3 quick examples. The first is about non-stationarity in lake and air temperatures. The second is about lake mixing depth and how we might think about lake system or sensors recording temperature. And then finally, I'll show an example using the leaf wax forward model about evaporative enrichment. So let's start with example 1. So one of the things we might want to know as we are looking at our paleoclimate data are questions like, oh, are lake temperatures faithfully recording air temperature changes? And is that relationship stable over time? We might be interested in the role of seasonality and mixing on our lake temperature proxies. And we have all the tools we need to evaluate these questions. We can use the lake proxy system model plus some paleoclimate time slice simulations to answer these questions about the relationship between air and lake temperature, as well as mixing depth. So what we did in this next application is we used a couple of the PMIP3 climate model simulations from GISS and HADGEM2, and we looked at different time slices, the historical, pre-industrial, mid-Holocene, and the last glacial maximum. To walk through this slowly, on the left here is a simulation seasonal cycle for air temperature. So these are the model inputs for the historical period in blue and the mid-Holocene in red. So this is air temperature at the site. If we calculate annual average air temperatures for Lake Tanganyika for this model, we get about 21.9 degrees Celsius for the historical and the same number for the mid-Holocene. So they're almost identical. However, if we look at the air temperature seasonal cycle, we can see that there's enhanced seasonality in the mid-Holocene compared to the historical period, driven by insolation forcing. How does that enhanced seasonality propagate into simulated lake temperature? So this right side shows the simulated lake surface temperature from the lake energy balance model. Again, historical period is in blue and the mid-Holocene is in red. And what we can see is that even though the annual average air temperatures for the historical and the mid-Holocene in this model are identical, the lake temperatures are hotter in the mid-Holocene, almost a degree hotter, despite the fact that there's no change in the air temperatures. So this is driven by the seasonality of air temperatures and how that forcing is applied to the lake system. And this is something we can quantify using the proxy system model. Now let's look at non-stationarity. So one of the questions I posed is, how does the relationship between lake surface temperature and air temperature vary over time? The left graph here is looking at PADCM3 simulated historical and last glacial maximum temperatures in the lake and the air. So what I'm showing here is the difference between air temperature and lake temperature for the historical period. This is the red box here. And then below is the difference between air and lake temperature for all of the PMIP3 models at the last glacial maximum. And so what we can see is that on average, the difference between air and lake temperatures in the historical period is about 5 degrees, but the difference between air and lake temperatures at the LGM is almost 6 degrees. So what we observe, at least for this particular climate model simulation, is that the lake is dampening the true air temperature change over time. So in this case, the lake surface temperature change is about 2.7 degrees Celsius. The air temperature change is about 3.6 degrees Celsius. And the difference that we observe over this time period between the air and lake temperatures is almost a degree. So not only is the lake and air temperature difference changing over time, but we also see evidence of the lake system changing or damping and altering the true air temperature change. And these are things we can quantify using the lake energy balance model. Here's another example with the GISS climate model. So in this case, on the left, we're looking at the historical period, and on the right, we're looking at the last glacial maximum. On the left box plot is showing the 2-meter air temperature, and on the right is showing the lake surface temperature. Again, we see a difference between the air and the lake temperatures for the historical period versus the LGM. And we also see that the change in lake temperature is much less than the change in air temperature for this model. So these, again, are the kinds of questions that we can look into about how climate is being affected by our proxy system. As a second example, we might be interested in how lake mixing depths affect our proxies that are recording temperature. So the lake energy balance model, as Carrie mentioned, simulates mixing depths over time. So this plot on the left is showing simulated mixing depth for the HADGEM2 model, for the mid-Holocene in red, and the historical period in blue during different parts of the year. So this is January to November. This model output shows that for this model, the mid-Holocene mixed layer depth is shallower during these months around May to July or August than the historical simulation. We can also see if we run other climate model simulations, for example, over the Holocene. This is an example with TRACE, where we simulated mixing depth over the Holocene from 10,000 years ago to about 4,000 years ago. And we see this non-stationarity in mixing depth. I apologize, the screen got a little weird with this y-axis, but suffice it to say, we see this jump around 5.5 kiloyears BP, where the mixing depth is shallowing in this simulation. And non-stationarity in mixing depths might be important for proxy interpretation. Why? Because, for example, GDGT production occurs in the suboxic zone. So if there's a change in the mixed layer depth, how might that alter the temperatures we record, and by how much? So in the past, we did some sensitivity experiments to understand what changes mixing depth over time. So here's our happy scientist, hopefully on a lake on a nice day with their Secchi disc, measuring light penetration into a lake. And we know that mixed layer depth is a function of temperature, as well as this shortwave radiation, visible light penetration to different depths. Wind speed, humidity, and evaporation also all control mixing depth. But we can do some controlled experiments with the model to see how, for example, the shortwave extinction coefficient in the lake affects mixing depth. Here is a series of experiments where we changed the shortwave extinction coefficient. And we know that there might have been greater shortwave forcing at the mid-Holocene in some of these lake sites, again, due to insulation forcing. That might lead to deeper light penetration in these lakes and a lower extinction coefficient. And indeed, what we find is as we change the depth to which light can penetrate in these lakes, there's a large change in the seasonal mixing depth. Now, why does this matter? Why do these changes in mixing depth affect our proxy interpretation? Well, consider the following example. Here I'm showing a temperature profile for a simulated lake. So this is January to December, and depth in the lake in meters on the y-axis. Temperature is shown with the color scale on the right color bar here. So in the first case, let's assume that temperature remains constant, but there's a shift in the mixing depth over time. If production of GDGTs or some other proxy that's sensitive to this mixing depth temperature is moving up and down in the water column, we would record a change in temperature as we move up and down in this water column, even though the temperature stays constant. In a second case, perhaps there's some multivariate nonlinear response to forcings other than temperature. We just saw how shortwave radiation forcing and changes in light penetration can alter mixing depth independently of temperature. We might have a change in wind speed that occurs independently of temperature. Let's walk through how that could change our interpretation. In the one case here on the bottom, let's say the mixing depth does not change in the black line. Then, if the temperature of the water is raised by 2 degrees via climate forcings, we're going to capture that. However, if the mixing depth gets shallower, we might be in a warmer section of the water. We'd get an amplified temperature signal. And if the mixing depth for some reason decreases, we'd get a damped temperature signal. And so these are, again, different uncertainties that affect our interpretation. This is, of course, tricky because we would need an independent proxy for mixed layer depth to quantify absolute temperature changes. And it's often very difficult to directly estimate changes in mixing depth independently. So again, the model just provides a flight simulator of sorts that allows us to try to think through all of the ways that our interpretation might be affected by these uncertainties. As a third example, earlier in the webinar, I introduced the forward model for leaf wax hydrogen isotope ratios. So this forward model takes precipitation delta D and translates it to wax delta D. But there are multiple conversions that occur in that transformation. So we know that precipitation will first enter the soil water. It will then be taken up by plants and be converted to xylem water. Finally, it will be converted into leaf water and leaf wax delta D. We know that various fractionations occur along the way due to both physical and biological processes. In climate models, specifically in the community Earth system land model, we can actually directly simulate soil water delta D and xylem water delta D. And we can test the impacts of assuming that precipitation delta D is the same as xylem water delta D. On the right panel here of this map, and this is the paper citation on the bottom left, I'm showing the difference between delta D of wax if we predict that value using xylem water versus if we predict it using precipitation. And as you can see, the difference between using xylem water as an input and using the delta D of precipitation as an input is quite large. So the color bar here is the forward model delta D of wax for the xylem water estimate minus the precipitation estimate. Notably, you can see that in regions that have high evaporation in the subtropics, we tend to see a very large difference in the predicted delta D of wax compared to areas where evaporative enrichment might not be such a big factor. So this is just another example of how we can use proxy system models to test our assumptions about our interpretations. So now we're going to briefly introduce the breakout rooms. And after we introduce each breakout room, which I think it's great that we have lots of time for this because I know you all have questions, and we can hopefully, all unmute and talk as a group in these breakout rooms. So I'm going to have each person introduce their breakout room one at a time. And we are going to take about a 15-minute coffee break after this introduction, and then we'll assign a time to come back. We're running a little ahead of schedule, and since time is money, we can obviously wrap up earlier, which is great. So I'm going to have us introduce for the next 3 minutes or so all the breakout rooms, and then we'll take a 10-minute break and we'll come back. So I'll go ahead and start by inviting Yu Yang to introduce his breakout room.
Yeah, if anyone have questions about the executable files in Mac and Windows, yeah, you can join this breakout room. Yeah.
Okay, Jim.
Hi, I'm probably not the person to try to join if you want to learn exactly how to run the model, but if you're kind of interested in thinking about the kinds of questions you can answer about lake systems using the model, I'm very, very happy to answer those and hope I can help. I would say too, I assume, Sylvia, it's okay for people to kind of go between breakout groups if they want. Yeah.
Absolutely. So you can visit as many breakout rooms as you like until we conclude. Carrie, do you want to introduce your breakout room?
Sure. Yeah, the topic of mine is lake modeling and paleoclimate modeling. So I'd be happy to talk about things related to the lake environment model, maybe how it's applicable to specific lakes or questions. Topics about calibrating lake parameters or uncertainty in the environment model, combining the environment model with paleoclimate output, topics like that.
Great. And then I will be in room 4. Really, you can ask me anything, but if you want to talk through various components of the proxy system model, understanding uncertainties or building your own proxy system model and scientific question design broadly, using this entire modeling platform, I'm very happy to answer those questions. So.